Okay, we are live. Let's take a look. The previous section we read last stream. So there's a couple days past, so let's refresh in memory. It was the ownership, there was stack and heap explanation. The ownership rules is each value in Rust has an owner. Then can only be one owner at a time. Then the owner goes out of scope, the value will be dropped. The scopes. Okay, string types, memory allocation. So yeah, move, charm. So there is deep copy. Any automatic copy can be assumed to be inexpensive in terms of runtime performance. Stack only data copy. Take ownership. And as no more valid, okay. But this is too much ceremony and a lot of work for the concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership called references. Okay. And now we can move to the references and borrowing section. The issue with the tuple code in listing 4.5 is that we had to return the string to the calling function, so we can still use the string after the call to the calculation length, because the string was moved into calculate length. Instead, we can provide a reference to the string value. A reference is like a pointer in that it's an address we can follow to access the data stored at the address. The data is owned by some other value, by some other variable. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type for the life of that reference. Here is how you would define and use calculate length function that has a reference to an object as a parameter instead of taking ownership of the value. So what we see here, we add ampersand and there and here, and then we can return length, and we still can use S1. So yeah, let's try this example. just delete everything here. Let s1 string from hello, and let len calculate len, and we need to define this. Sorry, I did it in the wrong way. So str ampersand string, and we can return what is wrong. Oh, we need to no usize. Okay, usize is pointer size unsigned integer type. The size of this primitive is how many bytes it takes to reference any location in memory. For example, on a 32-bit target, this is 4 byte, and on 64-bit target, this is 8 byte. So basically, yeah, it depends on architecture. I think this is clear, and now we can test it like this. Okay, we can delete this one as well. Run. So yeah, everything is working, but let's back for a minute to what we just read. Previously, if we pass the variable as without reference, it will become invalid and we cannot use it here. And the ownership come to this function, and if we not return it, it will be invalidated, and we basically lost access to it. Now we can pass the reference, so basically to the pointer in the heap memory, and the ownership will stay with s1 variable. Okay. First notice first notice that all the tuple code in the variable declaration and the function return value is gone. Yeah, it was return tuple in the listing. Yeah, for 5 we have this return tuple, but now we don't need to return it anymore because we didn't move our ownership. And the function return value is gone. Second, note that we pass %s1 reference into calculate length, and in its definition we take %string rather than string. These ampersands represent references and they allow you to refer to some value without taking ownership of it. Figure 4.5 depicts this concept. So we have the pointer, what is okay, s is here. So basically s1 is pointer, length and capacity, and s have the pointer, which basically pointer from the s1, okay. Note, the opposite of referencing by using ampersand is dereferencing, which is accomplished with the dereference operator, this star operator. We'll see some use of the reference operator in chapter 8 and discuss details of the referencing in chapter 15. So as usually, we knew it exists, we will learn about it later, but now just move on. Let's take a closer look at the function call here. Okay, the %s1 syntax let us create a reference that refers to the value of s1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference stops being used. So yeah, here scope definished. Yeah, s is the reference to a string. Here is goes out of scope, but because it does not have ownership of what it refers to, it's not dropped. Okay. Likewise, the signature of the function uses ampersand to indicate that the type of a parameter s is a reference. Let's add some explanatory annotation. Yeah, we just read it. The scope in which the variable s is valid is the same as any function parameter scope, but the value pointed to by the reference is not dropped when s stops being used. Because s doesn't have ownership, yeah, that's the menu. When the function leaves references as parameter instead of the actual values, we won't need to return the values in order to give back ownership, because we never had ownership. Yeah, basically same idea in all this description, like we don't pass the value, we pass the reference, so we don't move our ownership, so it's not dropped after the scope is done. And yeah, and we don't need to return ownership since we don't have it. We call the action of creating reference borrowing. Okay, so this is the term. What this is our previous description is borrowing. Is in real life, if a person owns something, you can borrow it from them. When you are done, you have to give it back. You don't own it. So what happens if we try to modify something we are borrowing? Try the code in listing 4.6. Spoiler alert, it doesn't work. Okay, but for sure we will try to do something with it, like push. So sorry. Let me just do cargo fmt first, and I guess I need switch buffer for a second. Yeah, now it's properly. Okay, I see some errors. Let me just restart the NVim. And what we wanted to do here is try to modify the string we borrowed. Okay, we have the error. Consider changing this to be a mutable reference. Cannot borrow the reference is mutable as it is behind reference. So the data it refers to cannot be borrowed as mutable. To be honest, I don't 100% understand what the error says, but yeah, let's read what the book said about it. Just as variables are immutable by default, so are references. We are not allowed to modify something we have a reference to. Okay, yeah, same as we have for variables, so nothing new for now. And here something interesting, immutable references. So can we actually mutate it? We can fix the code from listing 4.6 to allow us to modify a borrowed value with just a few small tweaks that use instead a mutable reference. So you see, now the string is mutable, reference is mutable. Let's try this one. So yeah, it looks like this, and it should be right here. So we directly specify when it's mutable, so we can pass it as immutable reference. So there is no confusion what type of reference it is, I guess. You should clearly specify that you wanna. So for example, this function is somewhere in different file, and we operate here and we pass s1 as reference. But yeah, I guess somewhere like C++ it will be mutable or immutable, and it will be no clear specifier. I guess maybe it's not true, maybe you can write something read-only or etc. But yeah, by default it's read-only, and if you want to mutate the reference you need to add mut. Let's take a look. So yeah, it's mutated, and after function we have mutated state. Okay, so far we are good. First we change s to be mutable, sorry. Then we create a mutable reference with ampersand mut s, where we can call the change function and update the function signature to accept a mutable reference with some string ampersand mutable string. This makes it very clear that the change function will mutate the value it borrows. Yeah, exactly. Exactly what we discussed. It adds some clarity to what we are doing. We're not just putting reference, we clearly say, is it read-only or it expected to be mutated. Mutable reference has one big restriction. If you have a mutable reference to a value, you can have no other reference to that value. This code that attempts to create two mutable references to s will fail. And of course we wanna try it. So r1 mute s1 as compiled suggest, and will it fail? No, it's not. It's actually interesting. Let's try. So you see we have okay, it's if we don't use r1 here, it's borrowed but then returned, but no, actually I don't really understand. Yeah, example pretty similar. Cannot borrow s as mutable more than one at a time. And what we have here, cannot borrow s1 as immutable because it also borrowed as mutable. There's a different error. So okay, let's try to recreate the error from the book first. And you actually see it not the different, it's the same error here. Let's try run explain as well. Variable was borrowed as mutable more than once. Please note that in Rust you can either have many immutable reference or one mutable reference. For more details you may want to read reference and borrowing section of the book. Okay, for more information we need to read the book, so let's back to the book. Cannot borrow s as mutable more than once at a time. Okay. This error says that the code is invalid because we cannot borrow s as mutable more than once at a time. The first mutable borrow is in R1 and must last until it's used in the println. But between the creation of the mutable reference and its usage, we try to create another mutable reference in R2 that borrowed the same data as R1. The restriction prevented multiple references to the same data as at the same time allow for mutation, but in very controlled fashion. It's something that new rusticians struggle with because most languages let you mutate whenever you like. Yeah, this is maybe something, we come to something very special about the Rust now, and something unique here. Basically that's why we're learning Rust, to learn some new concept, to understand how it's work, what the special about it. The benefit of having this restriction is that Rust can prevent data erase at compile time. Data erase is similar to erase condition and happen when the three behaviors occur. So let's read them. Two or more pointers access the same data at the same time. So I guess we need something like multi-threading for this. At least one of the pointers is being used to write to the data. At least one of the pointer is being used. Okay. There is no mechanism being used to synchronize to access to the data. So this is when data erase happened. At the same time we access same data, at least one of the pointers being used to write to the data, and there is no mechanism being used to synchronize access to the data. Okay, to be honest, I didn't totally get it yet, but maybe Next information will help me. Data races cause undefined behavior and can be difficult to diagnose and fix when you are trying to track them down at runtime. Rust prevents this problem by refusing to compile code with data races. Okay. Yeah, basically what I get from it, it's there is a class of problem exists, for example, now it's always compared to C++. For example, in C++ we have multithreading when we use some pointer in different thread and trying to access the data at the same time, and your app just crashed. But basically it crashed somewhere on, for example, user end, and you get report and you try it on your end, it's working fine, because yeah, multi-threading is hard to handle, like reproduce something and just running something in parallel, and how it will behave, it pretty random each time. So yeah, and basically this borrowing mutable reference once rule will prevent us from such kind of problems. I don't get these problems yet in details, but a general idea I get. As always, we can use curly brackets to create a new scope, allowing for multiple mutable reference, just not simultaneous one. So in this scope we borrow the reference, and after scope finished it goes away, and then we can do it again. And let's try to do something like this. Let's clear, let's format. Okay, I think we're still trying to do yeah, because we have ownership S1 and borrowing R1, and we're trying to use it at the same time. This is not allowed. But can we do like this? No, we still cannot do it. Why? So we can do it this way. Okay, so we borrowed it, we give it back, then we borrowed it again, and then we use it. And what we maybe can do here is this is how we have mutable variable, we create mutable reference, but borrowing is finished, we use borrowing here, and maybe we even can try to mutate. What is the issue here? Oh, I think it just something with LSP, so there is no actually an error. But if we try this, we will have the error, I guess. No, we will not. So only if we will try to use owner of the value and mutable reference at the same time. Cannot borrow S1 is immutable because it is also bird is mutable. So when we okay, we play a little bit with it. Let's restart. Not everything clear yet, but let's continue anyway. Rust enforces a similar rule for combining mutable and immutable reference. This code results in an error. So let's delete it and let's copy this one. Okay. Cannot borrow as mutable, it's also borrowed as immutable. So if we do borrow immutable, no other reference can be like whatever, mutable or immutable, I guess. I think over time those errors will make more sense to me. But for now, let's just continue. We also cannot have a multiple reference while we have an immutable one to the same value. Or of an immutable reference, don't expect the value to suddenly change out from under them. So this is the purpose. If we have immutable reference, we don't expect the value suddenly change. That's why we cannot create a mutable reference. Okay, makes sense. However, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else reading of the data. Yeah, makes sense. Note that a reference scope that starts from where it is introduced and continues. So the last time that reference is used. One more time, note that reference scope starts from where it is introduced and continues through the last time the reference is used. So we used R1, R2 here, but we don't try to use it somewhere after here, so it shouldn't be a problem. So let's just put it after println, we remove E, and here we should be fine. Cargo run, hello and hello, but then we can do and still we are fine. Okay, yeah, now it's look more comfortable. That it's doesn't mean if you do something in the scope we borrowed, then we cannot do something else after in the scope, but we just cannot mix the reference code start and finish with one, then switch to something else. Okay. The scopes of the immutable reference R1 and R2, and after the println, where they are last used, which is before the mutable reference R3. is created. The scopes don't overlap, so this code is allowed. The compiler can tell that the reference is no longer being used at a point before the end of the scope. Even through borrowing errors may be frustrating at times, remember that it's the Rust compiler pointing out a potential bug early at the compile time rather than at runtime time, and showing you exactly where the problem is. Then you don't have to track down why your data isn't what you thought it was. So yeah, basically the concept is the learning, write the code in strict rules which will avoid the problem for us. And this is, I think, main idea of the Rust so far, at least at the point we reached in the book. And dangling references. In the languages with pointers, it's easy to erroneously create dangling pointers, pointers that reference a location in memory that may have been given to someone else by freeing some memory while preserving a pointer to that memory. In Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before that reference to the data does. Let's try to create dangling reference to see how Rust prevents them with a compile time error. Yeah, let's just delete everything and paste it here, and try to compile. Missing lifetime specifier. This function return type contains a borrowed value, but there is no value for it to be borrowed from. Consider using the static lifetime. Alright. Yeah, exactly what error we saw. This error message referred to the feature we haven't covered yet, lifetimes. We'll discuss lifetime in detail in chapter 10, but if you disregard the parts about lifetimes, the method does contain the key to why this code is a problem. Yeah. This function return type contains a borrowed value, but there is no value for it to be borrowed from. Let's take a look once again. We're trying to borrow the value of variable s, which will be destroyed after the end of scope. So after we run the function, we try and borrow the value which should be destroyed, so it's not just a lot, so kind of clear. Let's take a closer look at exactly what happened at each stage of our Dangle code. Because S is created in some Dangle when the code of a Dangle is finished, S will be deallocated. But we try to return a reference to it. That means this reference would be pointing to an invalid string. That's not good. Rust won't let us do this. This solution here is to return the string directly. No Dangle. And here we move ownership of S fn no Dangle here. I guess we should be fine. Time to run. Okay, it's I guess complain about this piece. So if we run it again, yeah. We moved ownership of S to reference to nothing, and here we are fine. We can print it. This works without any problem. Ownership is moved out and nothing is deallocated. The rules of references. Let's recap what we discussed about the references. At any given time, you can have either one mutable reference or any number of immutable references. References must always be valid. Next, we will look at different kind of reference slices. Okay, more references. I think we will not dive into it today because it delayed already. It will be too much, I guess, to try and understand everything. But yeah, as always, we find out something new, we're excited, and I'm really waiting to move to this section, maybe tomorrow. Yeah, so thank you everyone, see you next time.